Second, if you missed the previous webinar in the series, or if you wish to share today's webinar with someone who couldn't join us today, remember that all of the webinar recordings are available for you to stream at your convenience on the AVIXA website. Lastly, we would love to hear from you today. Y'all have already done a great job of this. Please use the chat window to talk amongst yourselves and to talk to the AVIXA staff. But if you have a question, which we really hope that you have lots of questions about today's topic or anything for the panelists, then please use the Q&A window that is within Zoom. That way, our moderator today will be able to see them and ask them. If you don't have a question, but you do have an opinion, you can rank the questions in the Q&A box so that the favorite question from all of y'all is at the top of the list and is asked first. And with that, I'm going to go ahead and introduce our moderator and panelists today. Sarah Beth Mullins will be moderating the discussion. She's a doctoral student at Sorbonne University. Currently, she uses virtual reality to reconstruct the acoustic heritage of historic buildings. She has 3 years prior experience in audiovisual and acoustic consulting and is a 2016 recipient of the AVIXA Foundation's Michael Verkaufen Memorial Scholarship. She's joined today by our 2 panelists, Dr. Roger Schwenke, an honorary Mythbuster, and the senior scientist for Meyer Sound Laboratories, and Tony Spica, sales engineer for Audio Precision and Grass. I'll leave it to them to share a bit more about their experiences during the discussion, but please join me in welcoming them here today. Take it away, Sarah Beth.
Thanks, Michelle. Lovely to see you and Roger and Tony tonight. I am in France, so if you hear any nighttime noises, it's I'm afraid just a relic of my current physical location. I'd like to thank everyone for tuning in tonight. Having talked with Roger and Tony a little bit before the session, I'm really excited to hear what they have to say. So just a note or two about the format. Like Michelle said, please do submit your questions in the Q&A box. I'll be able to monitor that, and we'll be choosing the highly rated questions throughout the event today to ask to Roger and Tony as opportunity allows. They are also looking for questions throughout the entire portion, excuse me, of tonight's presentation. So please don't hold back or be shy about the questions you ask. Please continue to submit them as they go through both the prepared and the more ad hoc portions of the presentation. So without further ado, shall we jump right in? Tony, why don't you get started?
Okay. Thank you, Sarah Beth. I'm going to request control here of the presentation. Okay, so I thought we'd talk a little bit about the agenda for the webinar. I think the group is happy to keep it fairly informal. So if you have questions that are relevant as we talk about different topics, feel free to ask them. And as we're able, we'll be happy to address them as they come up. So first, we'll do a brief round of introductions. Both Roger and I will introduce ourselves briefly. Then I'm going to talk about, when we're talking about testing, or rather selecting a test signal, it's probably a good idea to know a little bit about test signals and their pros and cons. So I'm going to do kind of an overview of different commonly used audio test signals, a little bit about how they might be used or what we might think about when we're using them, how they're, what their pros and cons are. And then we'll talk a little about some important elements of test signals themselves. Roger's going to talk a little bit about crest factor and how we might think of that. And we might talk about some other things that you might want to consider when both making measurements, but also selecting what measurement stimuli are appropriate. And then we'll talk about some application-specific considerations as well. There should be time at the end for additional questions if we haven't had time to address them as they come up. So again, feel free to ask as we're going through stuff, but feel free to ask additional things at the end as there should be time. First, why don't we go ahead and introduce ourselves a little bit. Roger, do you want to introduce yourself?
Sure. So just recently, it was my 20th anniversary here at Meyer Sound. So I've been working on prediction and measurement of, in various situations for quite a long time here. Before that, I got my PhD at Penn State University. They're the only university in the United States that has a graduate department just in acoustics. At the graduate level, there's a couple other places to do acoustics. Other than that, and there also I was thinking about measurement.
Okay. Thank you, Roger. I'm Tony Spica. I'm a sales engineer for Audio Precision and Grass Sound and Vibration. If you're not familiar, Audio Precision makes renowned audio analyzers for a variety of different products, from audio amplifiers and related peripherals, but speakers and pretty much any kind of audio device. With the possible exception in the context of this conversation, we don't really do room analyzers per se, but anything that might go into a room might be tested with an AP product. Grass is a Danish manufacturer of a wide range of very good measurement microphones and related peripherals for both acoustics testing in general, but headsets and those kind of very specific types of devices. My career started in the automotive industry as an NVH engineer, which stands for noise, vibration, and harshness. And I worked for Brüel & Kjær for quite some time, dealing with a lot of different applications in both acoustics and vibration measurement. In my spare time, I'm what I call an audio electronics hobbyist, which means that I like to make little microphone amplifiers and EQs and such for music recording purposes. These days, I don't get a lot of that as I have 2 small children at home. So most of my dealings with, say, noise abatement is just to get children from stop screaming. So without much further ado, why don't we go on and talk a little bit about different types of test signals that we might encounter in the world of audio and acoustics, and how to think of them broadly. When talking about test signals, we might think of them in 2 separate groups. One being narrowband. And when we talk about narrowband, we're talking about a narrow range of frequencies that would be used in the stimulus. So typically, we're talking about sine tones. 1 kilohertz is commonly used as maybe the most basic sine tone stimulus that we might come across in the world of audio. But this could also be sort of a band limited noise excitation too. Depending on the application, you might think of that as narrowband. Most other things are what we might consider broadband. Broadband meaning they cover a wide range of frequencies. Sometimes that's 20 hertz to 20 kilohertz, which would cover the full audio band for human hearing. Sometimes it's say 100 hertz or so to 8 or 10 kilohertz, which would cover most of the range of the human voice, for example. So there are a lot of different types of audio signals that would be considered broadband type signals. The most basic audio test signal that we might think about is the sine tone. I think most people are familiar with what a sine tone is and what it sounds like. As I go through the different descriptions of the different test signals, I put together little pictures of what they look like both in the time domain. So at the left, there's a sort of an oscilloscope type view of what a sine tone would look like versus a short period of time. And at the right, I have a graphic representation of what it looks like in the frequency domain, meaning what frequencies are present when we're analyzing that signal in an FFT. Some things to note with the sine tone are that all the energy is at 1 frequency, which makes it very simple in a couple of regards. It's very easy to create a sine tone thinking in the analog signal generation domain. It's fairly easy to measure and to understand as well. With a sine tone, basically everything is at, from the stimulus is basically at 1 frequency, which means that if we filter out that frequency, everything that's left is noise and distortion. So in the history of audio and acoustics measurements, sine tones are pretty widely used in a lot of different domains because they're easy to analyze and fairly easy to understand. They have some drawbacks. One that we'll discuss a little bit as we go through is that, when we're measuring things like conference room audio or music playback, the signal that's typically going to be used with these things is not a sine tone, right? Normally, I don't know about you all, but normally when I'm trying to listen to music or discuss various topics with people, we're not listening to sine tones. So it's not really representative of the type of signal that these systems are designed to reproduce. But they can be very useful for diagnosing problems. As a quick audio example of what a sine tone is, I'm sure we're all familiar with what a sine tone is, but I've included some audio examples, so I thought might be good to share those. So you may have noticed, I don't know on your end, that the audio, or rather the sine tone itself may have been a little bit distorted, meaning that the level may have dipped in and out. It may have sounded like there were some harmonics present. And that's kind of a good illustration about the thing I was talking about, where the thing that we're calling on, Zoom, for example, is in an audio sense optimized to transmit speech. So as part of the thing where either there's background noise that is trying to attenuate, or things that aren't speech, it may be trying to attenuate through DSP things that it's not trying to broadcast, like a sine tone. So that could be contributing to the reason why it sounded poorly. So there are some, yeah.
Yeah, this is, so Zoom is basically going to be our example audio device for this presentation, and it's going to have an effect on our signals, the signals that we're talking about, and that's interesting. We're gonna this is about measuring different, choosing a test signal and measuring them and seeing what effect an audio system has on it, and Zoom is one of those audio systems. The other comment I'll make is that not all sine generators are the same. Something to watch out for. A little app on your phone or your computer may pre-calculate the sine tone and then generate other frequencies by just sort of resampling it. And that often causes, that'll show up as distortion at, if it's not an even multiple order divisor of that sine wave. So when you're analyzing this, if you're using a sine generator that's not from the analyzer, it's something to watch out for. You need to know the quality of your sine generators.
That's a great point, Roger. Thank you. And something that I think, for at least my section, I think I would emphasize two things. One, when we're thinking about selecting a test signal, we really want to think about what information are we trying to get from the test. So if we're trying to evaluate how well Zoom audio works for speech purposes, it might not be appropriate to try to evaluate it with a sine tone or a sine tone only. One thing we might do, and we'll discuss this in a couple of slides, is we might use actual speech signals in a transfer function type measurement as one of the primary metrics to evaluate, say, frequency response with speech through Zoom. Of course, there are a number of things involved, right? So I've got my headset, so that's a variable in the system. We've got whatever Zoom is doing. We've got whatever speakers or headset you're using to listen back. So there are a lot of things involved with how we're hearing audio right now. And Roger's point is very, very good about, not all signal generators are created the same. As an AP person, I'm glad that he said that, because I'm sort of in a position of bias here in the conversation, because AP is known for very, very clean, low distortion signal generators. And even with that, so in the slide here, you can see there are some artifacts present in the FFT of the sine tone. And this is an actual measurement that I made with a very good signal generator. And this is about as clean of a sine tone as you're ever going to see in the world for a real analog, both analyzer and signal generator. But you can still see a couple artifacts, right? These are very, very small. So the reference is, this is just a 1 volt sine tone. So in the dB world, it's at 0 for dBV. And the what we might call a second harmonic or subsequent tone at 2 kilohertz is minus 150 dB. It's very, very small. For most audio systems, this would never show up. It would never matter, but it's still there. And in signal generators that perform poorly, these are going to be, the artifacts are going to be much higher. So in addition to harmonic distortion, we have a couple what looks like power tones here, multiples of 60 hertz. So whenever we're making measurements, we're never measuring only one thing. there's always going to be some level of background noise at play that is going to be part of the signal that we're analyzing. So that could be from the signal generator itself in the acoustical domain, that could be from background noise and other things going on in the room, could be the background noise of our microphones. Even a good measurement microphone has a noise floor, right? So if we're measuring something that's very, very quiet, that might come into play. So there's all sorts of things we need to think about when we're actually making measurements. Maybe we'll go on. So, and there, I should say real quickly before we move on from sine tones, there are different ways to use a sine tone. So, commonly, certainly with a calibration tone, it's common to use 1 kilohertz, and 1 kilohertz is used for all sorts of reasons. Primarily that with different, say, frequency weightings, A weighting or unweighted or C weighted, which are different frequency weightings you may come across. 1 kilohertz is always the same with those different frequency weightings. Another reason why it might commonly be used, it's readily heard by people, even if they have some amount of hearing loss. Most people can hear 1 kilohertz very well, and in most say acoustical environments, the background noise at 1 kilohertz really isn't that high typically. So it's easily heard over say levels of background noise that are somewhat high, even in maybe industrial environments. So it's really good just as a quick, hey, is this working? 1 kilohertz works great for that. It also works great for some common audio metrics that we may come across, like, hey, what is, the most basic audio metric that you might see for anything is what is the distortion level or its max distortion level at 1 kilohertz, or what is the distortion level in terms of THD plus noise at a given, say, acoustical sound pressure level for a speaker or voltage out of an amplifier. So it can be very useful for comparing the performance of something versus a particular spec. One last thing I'll say about sine tones. One other way to use a sine tone is to sweep it. So if we want to look at what is the frequency response of a device, we could play multiple sine tones in succession and look at, say, the frequency response of something with many different individual sine tones. Oh, sorry. Did not mean to play 1K again for you. So one thing that's kind of similar to a sine tone, but is, say, a little bit newer in the world, and we're talking 10 to 15 years in terms of how long a chirp has been fairly popular. And a chirp is what you might consider to be a continuously varying sine sweep. A chirp has some distinct advantages. In that, in a very short excitation, there are virtually all frequencies present in the stimulus, from whatever low frequency we select to whatever high frequency we select. So the kind of comparison between that and a step sine sweep is that the step sine sweep is not hitting all frequencies unless you're taking a very, very long time to do it, like an infinite amount of time. So if there are particular problems in a audio device that we're trying to test that are specific to a single frequency or a couple different frequencies in the device, a step frequency sweep might miss them, or multi-tone might miss them, which we'll talk about in a second. The chirp is nice because we can also calculate THD versus frequency. It has some advantages in room acoustics as well, or speaker testing specifically, because one of the things that we can do with this technique is that we can remove acoustic reflections in the space. So one thing we might want to do with, say, a speaker test is we want to know what is the frequency response of the speaker itself, maybe separately from what the room is doing. And we can accomplish that with a chirp stimulus. In the frequency domain, it kind of has the shape of pink noise. So if we're looking at it in an FFT, it might not look flat. If we're looking at with an RTA or a third octave or nth octave band analyzer, it will look pretty flat. The analysis technique that's used with a chirp itself is actually a transfer function. So we're doing a cross-spectral calculation between what we're receiving and using the stimulus chirp as the reference. So we can calculate things like phase and magnitude and so forth very accurately.
Hey, Tony,
Yes.
You mentioned something earlier that I found interesting. Can you elaborate a bit more on how you might remove the room acoustic, for instance, reflections, from the signal when doing your post-processing analysis?
Sure. So I think on the next slide, I have an illustration of this. And one of the things that's computed when you do the transfer function of the chirp, and you can do this with some other things, but it's fairly common to have this capability with chirps, is that the impulse response of the system is calculated. And ideally, if there are no reflections acoustically, an ideal system will have a infinitely short and steep impulse at time 0 or whatever the propagation delay is in time. And after that, acoustic reflections would show up as subsequent impulses, as they are the same signal, but being reflected back and taking longer time to get back to the microphone. So what we can do is in the impulse response, window those out and recalculate the frequency response of the remaining impulse response. So what's shown here on the screen on the left is a measurement I made here in my home office of a pretty good pro audio loudspeaker. And if we were to look at this, the scale is somewhat zoomed in. It's only, it's about 20 dB of range there on the scale. But if we were trying to get some information about what is the frequency response of this speaker, I don't know if we can get a whole lot of reliable information from the response on the left. And this is not doing any windowing. This includes all the reflections in the space. When we start to remove the acoustic reflections, so start to window out reflections from the walls and the ceiling and so forth, we get a much smoother result. And it's maybe tough to see here, but it's from about 200 hertz to 10 kilohertz. This is plus or minus a dB, which is within the spec of the speaker. So you get a pretty reliable result, but not without having to do a whole lot. I mean, for speaker measurements and a lot of, say, device measurements, it's ideal to be in an anechoic chamber. But most times when we're measuring devices in rooms, we don't have that luxury. And we don't have the luxury of taking hours or days and weeks to treat the room so that we're measuring just the speaker on its own, right? We want to maybe consider the speaker on its own, but also consider the room and have limited amounts of time to do this. So the chirp technique, long story short, can get very good, reliable information in imperfect anechoic environments.
Great, thank you. That answered my question well.
Sure, maybe that's more than you had hoped. Maybe it's less, I don't know. Let's see, let's go to the next slide. One thing that's been particularly commonly discussed, at least in some of these standards bodies that I've been peripherally involved in, is the multi-tone stimulus. And multi-tone we can think of as multiple sine tones all played at the same time. So the main advantage of this is that it is very short in terms of test time compared to something like a step frequency sweep, or potentially shorter. One of the classic multi-tone examples is, these don't happen very commonly, but if you remember video test color pops that would have different test color bands, commonly multi-tone would be played as sort of the audio portion of that test, where say a TV station or other broadcasting organization could very quickly, test the quality of the video that they're transmitting as well as the audio in a very quick pop. I'll play an example of it. It's pretty, so far compared to the chirp and compared to Sine Tone, it's fairly exciting. So it sounds a little bit like your classic Sesame Street, the Count type Halloween scenario. So it's, if you're looking for a perfect Halloween sound for trick-or-treaters, multi-tone has you covered. One of the advantages of multi-tone is that, and I think Roger's going to talk a little bit more about this later, it has a higher crest factor than Sine Tone, and we can control it a little bit based on the phase and magnitude relationships between the different tones. So in a very quick burst, we can get a pretty good set of information about the frequency response of a thing because we have multiple frequencies present. And there's space such that we can calculate the distortion artifacts so that, if these were all, say, integer spacings, like 1 kilohertz, 2 kilohertz, 3 kilohertz, the harmonic distortion of 1 kilohertz would show up at 2 and 3 kilohertz and so on. So we would have no idea about what we're seeing in terms of, is it the stimulus or is it a harmonic distortion artifact? And multitone is spaced such that they're not at integer multiples. So we can identify anything that is not part of the stimulus as a distortion artifact.
Tony, just to loop back around to the previous slide, I've got a question from Thomas Stiles in the audience who wants to know, with a pre-measured or known speaker response, is it possible to determine the room response?
Sure. And, caveat here, I would say measuring room responses is not my area of expertise exactly. It's something I've thought about certainly, but not something I do a whole lot. But if you very confidently know what your stimulus is, then examining things that are, different than that stimulus, such as a room versus a speaker, that's certainly a very good starting point. If you don't know the response of the speaker, you could do a couple things. You could, one, measure that speaker, but you could measure both, say, a far field microphone and a near field microphone to the speaker and do a transfer function between them. And that would start to give you some idea of, it's very literally telling you what is the difference from in front of the speaker, very close to it, versus further out into the space. So I think generally speaking, in the broader world of test and measurement, if you are very confident about what your stimulus is and what it's putting into, say, the test device, whether it's a room or an amplifier or any kind of audio device, that is a very good starting point for understanding the thing that you're testing.
That is something I've done actually, in that I seem to be doing more and more often, is measuring quite close to a speaker in a room, and then gradually moving the microphone further and further away. And I found it quite surprising actually how close you can get to a speaker and still be able to see what the speaker is really doing, what the speaker as a whole is doing. Of course, it's got multiple drivers in it and a crossover and so on. But you can get relatively close to a speaker and get a very good idea of what it's doing, and then as you move away, you'll see more of what's happening in the room. Now, typically, what you want to know about a room is, how much absorption is in the room. What's the reverb? Does it need more or less absorption in it? And then also, are there problematic reflections? Are there reflections that you hear, distinctly? And usually, then you're looking at the impulse response, and the either for individual reflections in the impulse response or for the overall slope of how quickly are those reflections reducing with time. And that kind of, your reverb time versus frequency is that's sort of getting at what the original question is. You're kind of normalizing out the response of the source when you find that slope. And that is something I've seen some confusion about. Some people will I've seen people take a time frequency plot. So one of these color plots where you have time on one axis and frequency on the other axis. And try to discern the reverb time versus frequency of that. And that doesn't quite work because you're not normalizing it to the I'm not aware of any analyzer that will do that plot and also normalize it to the direct sound. Whereas instead, most analyzers that'll show you reverb time as a function of frequency, they're finding the slope of that reverberation time, and that does effectively normalize out the source.
Great. Well, I hope that answered Thomas's question. Let's continue.
Sure. Thank you, Sarah Beth. I saw a couple questions come in that I think I haven't had a chance to address. So there's one that's interesting from Joe that sort of, to sum up the question, some of these tests are fairly easy, right? Like figuring out what the distortion is of an audio device, including a speaker. It's a fairly straightforward test, but getting into sort of subjective evaluations or correlating that to, two things that sound, or rather test somewhat similarly, but sound different. Like, how do we quantify that? And maybe we can discuss that because it's fairly open-ended. Why don't we discuss that at the end? I would say, generally speaking, if you can hear a difference, then there should be some quantifiable difference, and maybe just the wrong tests are being employed. One of the other questions that came up, also from Joe, is that what are people using to set up and verify things like Teams and Zoom? And to be honest, I do not know. I have some ideas about what I would do, but maybe we can talk about that more in detail at the end. Why don't we talk about just two more test signals that we might use and consider, and then Roger will talk a little bit more about some other considerations. As I'm clicking through here, there was one additional question about what analyzer am I using to make these measurements. All of these are done with Audio Precision hardware and software. There's a little AP logo there at the top right. So including the speaker measurement that I made before. So that was just using AP hardware and analyzers and a grass measurement microphone. So a couple other things that we might consider, some additional broadband things that are kind of readily available, fairly simple, but more complex than a sine tone or multi-tone or a series of sine tones. Noise. So noise is a kind of a classic broadband signal, and we can think of noise in a couple different regards. Some common noise signals are white noise and pink noise, and the basic difference between those is pink noise is equal energy per octave. So if we're looking at, say, an RTA or a third octave band analyzer, it is flat in that regard. And if we're looking at an FFT, white noise is flat. It is equal energy per frequency. So to human hearing, white noise will sound like it has more high-end energy. Pink noise will sound flatter to the human auditory system. And oftentimes pink noise would be used for that reason. But white noise shows up flat on an FFT. So if you're using an FFT, white noise might be a little bit easier to get some information from. And noise are completely random signals. So it's energy equally distributed over time, but it's fairly random. So if we're looking at, say, the time domain in an oscilloscope type view, it's tough to get really any information about the signal then. We have no idea about, really its frequency response from looking at it. We have no idea about what frequencies are present, whether it's distorted at all. The time domain view of noise is typically difficult to look at least in short durations. I'm sure we've all heard this, but I'll play a little audio sample of pink noise real quickly. And Zoom is doing a fun thing there where I think they're trying to attenuate background noise from the speaker or whoever is talking. And you may have noticed that the volume dipped there a bit because the noise signal is kind of exactly the thing that it's trying to attenuate. So for complex systems like a smart device or this type of audio platform, noise might not be a great stimulus, other than if you're trying to evaluate how well is the attenuation working. And there's some different ways to go about that. If we're trying to compare, so this is pink noise shown just on an FFT in blue. So it would appear that the slope is going down. It would appear that there's less energy at high frequencies. But if we're looking at kind of in the orange poles there, that's a third octave band look at the energy, and it is flat with regard to third octave band representation. Another type of stimulus that we might use is music. Again, I said earlier that a lot of the things that we ultimately use in audio are designed or intended to transmit music or speech. So using music might make sense to use for that reason, is, in a lot of cases, the very thing that the device is intended to transmit. Some of the caveats are that, there's no obvious way to quantify the distortion that's present in music. Music will certainly have a broad range of frequencies. It's somewhat genre specific. I very intentionally don't have a audio sample of music because it would open me up to some amount of criticism probably. However, we can use a transfer function analyzer or analysis to compute things like frequency response, phase, coherence, while using music or speech. So if we're testing, say, a telephony system, we could use speech because it's the type of signal that telephone type systems are designed to transmit. And using a transfer function analysis, we can get a lot of good information from that and not be sort of held up by the fact that it's not flat in frequency. So that can be very useful for some complex devices. The last thing I'll talk about briefly, and this is something that Roger is much more familiar with, is a noise signal called M noise. And M noise is sort of audibly similar to pink noise. And what I have there in the frequency domain plot is in maroon a analysis of pink noise, and in blue is the M noise signal. I'll let Roger elaborate on this, but one of the kind of the characteristic things of M noise and its sort of advantage is that it is designed to have crest factors that are much more similar to music. So it's a much higher crest factor, especially at the higher frequencies, which make it much more similar to a music stimulus. The last thing I'll say, just maybe in the interest of time, because I'm just rambling, or at least going at length when I should not be probably. So in some additional things to think about, Roger pointed this out earlier, we want to think about the quality of the signal we're generating, and we want to think about the quality of the signal from an analyzer side. If we put garbage into a test, we're going to get a garbage result out. So we want to think of, if it's an acoustics test, we want to make sure that our microphone is calibrated, that it's a quality measurement microphone. We want to make sure that the signal we're generating is clean and not distorted otherwise. These are things that you guys as professionals probably think about all the time, but it's worth reiterating. And to sort of sum up, when selecting a test signal, I think in any kind of test, we always want to think about what information are we trying to get from the test. Are we trying to compare to a particular specification? Are we trying to get some information about what the room is doing acoustically? Are we trying to measure just the speaker on its own? Are we trying to evaluate the device for how well it transmits music or speech on its own? Those are the things that I typically think about when selecting a test signal. There is one question about what environmental factors might impact the choice of a test signal. And there are some things to think about. I think both in terms of like an acoustical environment. So if we're trying to eliminate that as a variable from the test, we might pick something like a chirp, where we can window out acoustic reflections. If we're trying to consider the whole room as part of the system, we might use a broadband excitation like pink noise, for example, or some other things. One thing that might, the performance of things may change over time as well. So heat can be a consideration. Do we want to stress an amplifier speaker system with heat considerations, and how does it perform over time with a certain type of test signal? So that's something we might want to think about also.
Thanks, Tony. I see we have a couple of quick questions related to your overview, and then I'd like to turn to Roger. But real quickly, do you know what frequencies were used in the multi-tone example you played earlier?
Yeah, I don't know off the top of my head. I could probably pull it up while we're talking about it. It's you can use a wide range of number of tones. In that particular example, it's kind of a standard AP 32 tone set, but commonly people will use 7 tones or 5, or you can make your own set. The frequencies, I think, are intended to be, somewhat octave band aligned, but not integer aligned or mathematically aligned, such that determining distortion is impossible.
Right. Jade asks if there's a reason why we see pink noise being used more than white noise, and wonders if it's because it mimics human hearing more accurately.
Yeah, I mean, I think that's the fundamental reason. I think that's exactly it. If you had to sum it up
I,
for one particular
I can
reason.
think of a couple factors. So doing a transfer function is pretty easy nowadays, but digital things develop very rapidly, and it wasn't that long ago that a transfer function was pretty difficult. But a third octave band analyzer was, pretty ubiquitous. And if you play pink noise and look at it in a third octave band equalizer, it'll look flat, and we'll see that in my slides in a minute. So that's a motivation. The other motivation is that white noise has equal energy per frequency. So there's the same, if you have energy up to 20 kilohertz, there's the same energy between 10 kilohertz and 20 kilohertz as there is between 0 and 10 kilohertz. And there's twice as much energy from 5 kilohertz to 20 kilohertz as there is from 0 to 5 kilohertz. So if you're interested in making a high signal to noise ratio measurement of a woofer or a subwoofer, then white noise is going to put a pretty tiny fraction of its energy at those frequencies, whereas pink noise does a better job of distributing the signal to noise ratio fairly over the frequencies that we care about.
Great.
Yeah, that's a great point.
Yeah. Well, in the interest of time, why don't we pivot to Roger's presentation, and we'll get to more questions after he finishes speaking.
Okay, I did the request control the screen thing.
Yes, it says that you should have control.
Okay. All right, so I'm going to start off with a pretty simple display here. This is just a meter, and like a lot of meters, the time-weighted RMS level is shown as a solid bar. And then we've got this little thin bar above that to show the peak level. And then a second thin bar above that to hold the highest peak level. And if you don't have a meter like this, a sine tone is useful, because a sine tone will, light up your meter, very constantly and at a high level. But a sine tone, unfortunately, is not great for measuring the capacity of loudspeakers. So at low frequencies, below resonance, they're typically peak limited loudspeaker drivers, but above resonance, they're typically RMS level limited and have much higher peak capacity than RMS capacity. And of course, real loudspeakers are often made of multiple drivers and have crossovers, and so the actual headroom, both peak and RMS level of a loudspeaker, is quite complicated. It's not just a single number. So then how do you measure, like, what's the maximum capacity of a loudspeaker for real signals? And really the answer is that it's a different number for every signal. But it's definitely different for speech and music than it is for a sine tone or a sine sweep. And so unfortunately, a sine tone and a sine sweep are not great for telling you the max SPL of a speaker for real signals. And pink noise could be better as well. And this is just a quick demonstration of that. So here we're showing the RMS and the peak levels on the top. We're showing pink noise on the bottom. We're showing music. And then we're also showing a filter. So this is low pass at a kilohertz. So below a kilohertz, the RMS and peak level of pink noise in music is pretty similar. So I'll go ahead and play this for a while, and we'll see that they're roughly similar. And I will switch the filter to be a high pass filter. And what we'll see very quickly is that the music has much higher peak levels at high frequencies and somewhat lower RMS levels at high frequencies. And it's vastly different from pink noise. So we wanted a signal that was better. And in fact, there are signals, standards bodies have developed signals, they're usually called simulated program noise, that have an RMS level that roll off with frequency. But unfortunately, the peak levels also roll off, and I'll show that. So we did an analysis of a very large number of signals. I'm actually not showing them, all of them here. We analyzed hundreds of tracks of a great variety of musical styles and sources. And these are these gray lines here, and this is the RMS level. And you can see pretty roughly that above 500 hertz, the RMS levels start to roll off for real signals. Whereas pink noise, which is, I've tried to graph it in a roughly pink color here, is equal levels in octave band. So on this graph, I've passed the signal through an octave band filter, and I measure the RMS level of the output of that filter, which is different from what we saw previously. So what we saw previously, we were looking at individual FFT lines. And so pink noise doesn't look flat when you look at just a raw FFT. So here I'm looking at the output of filters. So pink noise looks flat. So M noise, just this signal we came up with, is similar to pink noise at low frequencies, and then the RMS level rolls off at high frequencies. And this red curve here is a signal called 426B, which some standard body decided was a good representation of music, and it does roll off at high frequencies like real signals do. And it also has sort of a high pass characteristics. The levels are lower at low frequencies, like some music is, but not all signals. So that looks pretty good for RMS levels, but what about peak levels? What about crest factor? What's different about M noise than this other simulated program signals? Well, so now we took the output of those octave band filters and we looked at the peak levels. What is the peak levels in the output of those filters? And so those same real signals, those levels typically don't roll off at high. Those peak levels do not roll off with high frequencies. The peak levels remain relatively constant. And if you look at pink noise also does that. Pink noise has relatively constant. I expected it to be quite dramatic, actually. Your intuition is that crest factor should increase with frequency, and you can see a little bit of a slope here to pink noise. But really, if you look, tip to tail, it's really, minus a dB at the bottom and plus a dB at the top. It's, you can also say the peak levels are flat as a function of frequency, plus or minus a dB. And so that's how we designed M noise. So M noise has relatively constant peak levels as a function of frequency, like pink noise. I'm going to go backward. I'm going to try to go backwards a slide here. Oops, I can't do that. I'm trying to use my left arrow. Well, so in the previous slide, you saw that. There we go. The RMS level of M noise rolls off like other simulated program signals, and unlike pink noise. And then if we go one forward here, the peak levels of M noise are constant, like pink noise, but unlike other simulated program signals. So what we're trying to do the best of both worlds here. And we're hoping we think that is more like what real signals are. Real signals have peak levels that are relatively constant with frequency, but RMS levels that roll off.
Hey, Roger, a quick question from the audience. They'd like to know what sort of music was used in this analysis. Was it classical or some other genre?
As many genres as possible. So yeah, there was classical music, there was jazz, there was rock, there was rap, there was electronic dance music. I can't. I have, you know, in the we did a paper. We've done a couple papers now describing it. The first one was for SIPD, and there's a list in that paper of all the different musical styles. And I'll also next I'll talk about speech and also cinema. So we also measured speech only signals, and we also measured raw cinema soundtracks, and there were so somewhat different, subtly different, but pretty much the same result. So now crest factor is the ratio of the peak and the RMS level. So the difference, so in decibels, it's the difference in decibels between the peak and the RMS level. So these are all plots in decibels, the vertical axis here. So now we can show the crest factor of this big plot is the crest factor for all of these signals. And we can see that the crest factor of pink noise and the classic simulated programming noise is pretty constant with frequency. It rises a dB or two, but that's about it. Whereas without exception, all of the signals that we measure, the crest factor rises significantly more, 10, 15 dB above what it is at around 500 hertz. And so that is how we design M noise, is to have a crest factor as a function of frequency, which rose dramatically. And we can look at speech. So speech, the RMS levels of high frequencies roll off significantly more. And this red curve here, ANSI 3.5, defines an average level of speech. And so we can see that corresponds pretty well with our analysis of speech. And here we can look at the peaks. And we can see that the peaks are higher than at higher frequencies than the average level. And so also in speech, also in pink noise, you can see in the SIMPY papers, the whole plots. At the crest factor, all of these signals, without exception, raises significantly with frequency much more than pink noise and other filtered noise signals. Okay, so now what do you do with that? How do you measure the headroom of the speaker with that? The way we do that is with a transfer function. So I'm about to show a little video of a procedure. And what we're going to be showing is a frequency response. We're going to show the ratio of the output of the speaker to the input of the speaker. And so there's, important thing about this graph is that it is the ratio. And so that it needs just, one step more thought to form your expectations about what's happening. So at the beginning, we're going to play M noise at a low level that we predict that we think the speaker can handle. And then we're going to increase the input level, and we hope that the output level will increase by the same amount. If the speaker is behaving well, the output will increase by the same amount. And so if the input and the output both increase by the same amount, and the frequency response is the ratio of those things, then the ratio should stay the same. The frequency response should stay exactly the same if it's performing linearly as you increase the signal level. So we'll do that. And of course, everything has a finite capacity. And so we'll keep turning up the signal level until at some point we'll increase the input level and the output level will not go up as much. And that's when we're hitting the headroom of the speaker. And that is when we'll see the transfer function change. So again, go ahead and start this video, and I'll try to, I don't know how well synchronized I'll be, but so this is our low level, and we've stored that level, and we're gonna recall that level down a couple dB So that's our threshold. Where, you know, if it changes more than that, then we're going to stop. So now we've increased the playback level, and it has, in fact, I'm going to pause the video now, actually. Oh, it's difficult to hit the pause button. So you'll see for the most of the beginning of that video, the frequency response stays the same. And then as we increase the level of, you know, to the very top there, you'll see the frequency response come down. I'll give it a start again. Okay, so here we are, we've increased the playback 17 dB, and our frequency response is solid, and now we're gonna keep increasing it. And we start to see around 250 hertz, we start to see that frequency response coming down. So that means that as we're turning up the input at all frequencies, the output is going up the same amount at all frequencies, except around 250 hertz is not quite keeping up. And so now the amount that it's come down has touched our target trace there. You know, we want it to change a reliably discernible amount. We want to be able to do this again and get the same number. And if you look for a tiny little change, then you're probably going to get a different number every time. So 2 dB is what we've found is a reliably noticeable change. It's also, even though it looks pretty dramatic in this frequency response, it's not a huge, you know, perceptually, it's not a huge difference. You can maybe hear it, but it's not a hugely objectionable change in the frequency response. So that we feel is a pretty good representation of what a speaker can do for real signals, and a transfer function can also do this for real signals. You can compare noise to measuring a speaker with a music track or a speech track that you like. What the advantage of M-Noise is that we all don't have to agree on the same style of music. It has statistical properties that we think hold over every style of music, more so than pink noise. So what I've shown here is the change in the frequency response, and also up here there's something called coherence. And coherence is, roughly speaking, a measure of the quality of the measurement. And there's a couple things that can reduce coherence. One is background noise. Usually you don't have that much of an issue with background noise when you're measuring max SPL. Another is reflection. So if there are light reflections arriving later than your analysis time, that can reduce coherence. So when you're doing these tests, it's beneficial to have your microphone very close. And then finally, the last thing that can reduce coherence is distortion. And so that's the benefit of having a relatively quiet space and having your microphone quite close when you have this test, is you can also look for distortion. And there we have seen speaker models where distortion happens before there's a significant change in the frequency response. And the coherence will show you that. If I can go, there we go. So here's a different speaker. And you can see that the frequency response has changed a little bit, but it hasn't come down the 2 dB that we consider our threshold. But up here, you can see the coherence has come down dramatically. And you can hear that if you play music at this level and you play it until you start to hear this coherence come down, the amount of distortion is definitely audible for this speaker. And so that's something that we found beneficial about calculating the frequency response, is not just the frequency response, but also the coherence can catch all the things that mic are wrong with the speaker might show that you've reached its capacity. I think we're at the hour now, so I think I'll
Oh, I was just going to pop up to say quick. Yes, we can keep rolling with information, but for the audience, if any of y'all need to leave, know that you will still receive your RU for staying until 2 o'clock. But you are welcome to stay because we'll keep rolling through any remaining questions. And Roger, I know you had a couple more slides, but yeah, just want to let you all know.
Well, mostly I had a couple more slides, in reserve in case people asked a question on that topic. So I think we should just get through people's questions at this point.
All right, we can do that. So I do actually have a question for you, Roger. This is mine, not the audience's, although I'm sure it's come up in someone's brain as well. When does the crest factor matter when I'm choosing a test signal? In some applications, surely crest factor becomes one of many parameters to be considered. And what points should it become the most relevant consideration?
Yeah, well, when it's it was designed for measuring the capacity of loudspeakers. So when you want to know what is the max SPL that a loudspeaker can reproduce linearly, for the types of signals that I'm actually going to use it for, that is what mNoise is designed for. And you can use it in other situations. You can use if you're calculating a frequency response, if you're doing a source-independent frequency response, you can use mNoise. You can use pink noise, or you can use music. That's what source-independent means. You can use any signal. So you could use mNoise for that, but you don't have to. But I have also found it useful, not just for speakers, but also for just audio devices. Looking at the coherence, if you want to play a signal at a representative level of real signals, you can do a frequency response, and you can look at the coherence, and it'll show you when you get to clipping, when you get to start clip and input. Now, using a sine tone or a multi-tone and looking at distortion, that will give you a much more sensitive measure of distortion, a much more, it'll get you, down to the 10th dB at what point does an input clip. But the RMS level of that signal is going to be very different than the RMS level of the actual signal that you're going to pass through the system. So I have, so if you're doing sort of a laboratory grade measurement, if you're in product development and you want to, get numbers to the 10th of a dB that you can put on a spec sheet, then, a THD with a sine wave will give you a very sensitive measurement. But if you're in the field and, ultimately you want to measure a frequency response with a broadband, with pink noise or mNoise, then yeah, you can use that same signal, that same analysis on the input side of things, and check that you're scaled reasonably. You can do it. You can do it there too, and I think that's an advantage to have, one signal and and one analysis that you can use, all over the place and get your system set up and scaled reasonably.
Makes sense. I see we've got several specific questions to mNoise. So if you don't mind, I think we'll continue to dig into this. Hidenori asks, for the application to live sound system tunings, they consider that mNoise is generally more for sound pressure level measurements and capabilities of the speakers, but not for actual system tuning process. And they would like to know if this is an accurate understanding of an application for mNoise.
Well, if you're doing a frequency response, so if you're looking at the ratio of the output to the input, then you can use M noise, or you can use music or any signal. Now, if you're doing, and this is a very old way of doing things, but if you're looking at a third octave, filters, if you're doing just a single, if you're just looking at the levels at the microphone and not comparing it to the input of the system, uh, then you would want to use pink noise, because pink noise has equal levels on a what I call band spectrum. Uh, now, if you do that, then you don't get to see what the phase is. You don't get to see what the coherence is. You don't get to see if there are interfering reflections that are causing that are affecting your measurement. If it's really um, the system. So it really depends on if you're looking what I call single-ended. If you're just looking at the microphone of the signal, then there is some reason to use pink noise. Whereas if you're looking at the ratio of the output to the input, some people call it the word transfer function. I think is the most unambiguous. If you're doing a transfer function, then you should be able to use any measurement and any signal, and then M noise is a reasonable signal to use there also.
Great. Juan asks what the difference between peak and crest measures are. Could you go over that again?
Sure. So the peak is you pass the signal through a filter. So we have an octave band filter, and whatever the maximum level that achieves for any small, no matter how short a time, that is the peak level. Whereas crest factor is the difference between the peak level and the RMS level. So a sine tone of the difference between the peak and the RMS is always the same. It's always 3 dB. And then as you add more tones, your peak will go up faster than the RMS. So a multi-tone with a large number of tones might be 10, 11, 12 dB. And most test signals are 12 dB. And difference between the peak and the RMS. And then M noise for the whole bandwidth. If you just look at the raw signal in the time domain, that's 18 dB. And then what's different about it is that if you look at it as a function of frequency, if you look at it in octave or fractional octave bands, it's different in different fractional octave bands. And that is what real signals are like. And so that's the benefit we see in it as a test signal.
An anonymous attendee would like to know how you'd compare this measurement method with the maximum input voltage measurement method for the common loudspeaker common loudspeaker format. To this person, MIV seems to make sense because electrical pressure is compared to the acoustic pressure coming out of the system. Could you speak a little bit about the comparisons?
It's been a long time, unfortunately, since I looked at the CLF specification. If it's anything like AES2 is pretty similar to the M noise procedure in that you play your test signal at a low level and get your frequency response, and you turn it up until the frequency response changes. AES2 only has about a paragraph about that. So that doesn't go into tremendous detail. Whereas there's a written procedure that accompanies the M noise signal. And if I can go to the next slide, I think it'll show a screenshot of the web page. So it's accompanied with the procedure, and that's a little bit longer and goes into quite a bit more detail um, than you would see that's currently in AES2. So I think the idea of finding the maximum input voltage by looking at a change in the frequency response, that's not really entirely new. We've provided a lot more details about how to do that repeatably than previously. What's really new is a signal that has the statistical properties of real signals. So using that procedure with a signal that has a crest factor that changes with frequency, like speech and like music, that's the part that's very new. And I saw in the questions there's a question about what the M stands for, and we've made a little bit of an effort to have it not stand for Meyer. We made a separate web page for mnoise, mnoise.org, where you can get the signal and the procedure. It's freely available, so it's open to the public for people to use, for anyone to use. So yeah, we're trying to make it not specific to us and our products.
That actually, I think, touches on a question from Joe Nickel, who would like to know if mnoise is going to be released as an open source. I think you just answered that, yes?
It is. Well, I'm not a lawyer, so I can't get into the very finest distinctions. I believe it's currently released for individual use, so you can as an individual you can do what you want with it. If you want to incorporate it into a product, so if you're building an analyzer and you want to incorporate mnoise into your analyzer, we want you to do that, but we also want you to talk to us when you do that. So there's a little bit in the license there. And we are also working with, we've announced recently, actually, we're talking with a couple different standards bodies about mnoise. So AVIXA has the dynamic range group, where we're looking at not just the max SBL, but also the noise for the whole gain structure through a system, and mnoise is going to be an option there. And we're also talking to AES, and AES, the hope there is for eventually mnoise will be available from the AES, so it'll be a neutral third party that can provide mnoise to everybody. But right now, it's already available to everybody, and it's quite liberal what you're allowed to do with it as an individual.
Right, that makes sense. I've got a couple more specific mnoise questions, and then I'd like to loop Tony back in for a few more generalized questions. But real quick, Robert Pelletier asks, do you ever see loudspeaker failure before the mnoise tests returns as nonlinear?
I personally have not, and that is part of what we're doing with AES is to make sure that other manufacturers agree that a 2 dB change is non-destructive. And that's part of what we're hoping to do in the industry is to have an agreed upon signal and agreed upon procedure, so that a manufacturer can say, this is the maximum SPL that the speaker can reproduce with the signal, and then the person who buys it can then play that signal and get that level without fear that they're going to break the speaker. It's kind of weird, honestly, that in the audio industry, we fear breaking our speakers. Like we're concerned I might turn this signal up too loud. It doesn't happen with video. like no one ever worries that, oh, I might play this TV show too bright and break my television. Or if you get like an LED light bulb with Wi-Fi and you can like change the brightness and the color, nobody ever worries about the dimmer knob on their wall turning it up too bright and burning out the bulb. But somehow that's the situation we're in the audio industry, and so that's something we're trying to help fix. Like if we have this signal and this procedure, then hopefully manufacturers will start providing that number, and then people can confirm that, without fear of possibly damaging the device.
Yeah, I think you raise a great point about comparability between our industry and some of our related ones. Here's another question from Joe Nickel. He'd like to know, does M-Noise document what we hear as harshness in some drivers, especially at louder sustained levels?
If you see the coherence reduce, if you have your microphone close enough and you see your coherence reduce, that is caused by distortion in the speaker, and you will hear that as harshness. And we think that's a good way of designating the max performance of a speaker. Now there are other methods and other signals and analyses that are much more sensitive. So if you do a multitone, you can see distortion products that are 50, 60 dB down, much lower. So there are other ways of measuring harshness that are much more sensitive, and that can show you that it's happening before it's actually audible. So we don't claim to be a high sensitivity indicator of harshness, but you will eventually see it if that happens and you turn it up loud enough. You will eventually see it in the coherence.
So I do think that sort of leads into a more general question that Joe submitted earlier in today's webinar. Tony, I'd love for you to jump in on this too. It's a bit of a long one, so bear with me as I read his background. He says, a lot of the signals and tests we use are quote unquote easy and repeatable, but don't really tell us much about the perceived audio quality of a system. Examples given include frequency response, distortion, signal to noise, things like that. It's not easy to measure the difference between a mic pre on a Mackie mixer and a 2K outboard mic pre. And he seems to recall that a few years ago, Dean Jensen wrote an article about spectral contamination where he proposed the use of what Joe recalls is a multiple sine wave. He'd like to know if you think there's a test or a measurement that should be added to our standard toolkit that could provide better insights into audio quality.
Sure. So can you guys still hear me?
Yes.
Yep.
Okay, great. Sorry, I had to swap out headsets there for a battery issue. So this is a fairly potentially complicated topic and something that people could talk about probably for hours. But I think to answer your question directly in kind of in two different aspects. So for general AV applications, I don't know if there's a sort of a ready-made test that looks at, say, sound quality specifically, or at least that would, provides a lot of value. Now, that being said, I think I mentioned before in the presentation that generally speaking, if you can hear a difference, you should be able to quantify it objectively. Now, it could be that we're looking at the wrong metrics if we don't see, it's sort of general THD plus noise type, say, measurements. Maybe we're not going to see much difference between, say, a Mackie mixer and a $2,000 outboard mic pre. However, perhaps if we started looking at other things like upper order harmonics or intermodulation distortion, I think we would start to see some differences. Like that sort of thing is very difficult to quantify, though, in terms of audio quality. Now, from a different perspective, speech quality is something that there are a couple things that are commonly used in the world of communication. One of which tries to look at and quantify, it's called Polka, and it tries to effectively take what is a jury pool type test, where you hear a bunch of actual speech signals played through a device like maybe Zoom, for example, or a smart speaker or something, record those back and compare them to the original signal. I apologize if there's a little bit of background noise. As a function of COVID, my wife and I are both sharing an office at the moment, and she had a meeting that started at 11. So sorry about the background noise if there is some. For speech examples, though, there's this technique called Polka, which uses speech signals through any kind of audio device to evaluate sort of on a scale of 0 to 5, 5 being good speech quality, 0 being absolutely poor speech quality, to make it very simple to objectively and repeatedly have very good correlation to subjective jury pool tests. And similar things don't really, don't exist broadly speaking for the types of pro audio devices that Joe's talking about. There are some things that we can do where, if you want to first, something I would think about is, if you want to very clearly establish that there is a quality difference, make some very well-controlled recordings through both of those devices and do some double-blind jury testing with actual people. And if people can then, in a very well-controlled double-blind sort of study, identify the pre's consistently, then there is a difference. And if there's that kind of difference, you should be able to objectively measure them in some way.
Roger, do you have anything to add to that?
Yeah, well, I think that there is, even though we're excited about M-Noise and we're hoping that a lot of people use it, especially the loudspeaker manufacturers. I think multitone has a lot of potential, and I'm glad that it's available in some analyzers, and I'm glad that people are. It's a very sensitive test, but I think what's missing is indicated by the conversation so far is the connection to audibility. So which harmonic distortions are more objectionable than others, and which ones are really an indicator of audible quality. They're not all equally detrimental to quality. So the multitone is a great idea, and it's available in some analyzers, but I think it's going to take some time before we really connect it to to make something that has a reasonably high crest factor and know how to analyze it in a way that is more directly correlated with subjective quality.
Do you think there's a chance that manufacturers are going to adapt some consistent or uniform standard of audio quality across their products? Is that too speculative of a question?
Well, I think so enough that we're trying. We're putting effort into it. We're talking to standards bodies to make it a standard, not just a thing on a website, but part of a standard. And I think people can make a difference. If the people in this webinar go download the signal and try it, if they measure a device and email the manufacturer and said, I got this number with M-Noise, is that what I should get? It's there's sort of a crowdsourcing aspect of this. We're hoping we're hoping from support from all sides, and not just that other manufacturers will participate, but so the intention is to make it independently verifiable, that the people who are buying the product can do this test and confirm it. And if they do, the more they do that, the more it will motivate the manufacturers to provide that number.
Great. Tony, do you feel like that's an accurate view of where we're heading?
I think that's a good point. And I think outside of sort of the AV conversation, some industries have sort of, for example, telephony, like I mentioned with the Polka, it's not really a standard per se, but in an R&D sense, people are doing it pretty consistently for telecommunication devices. I think Roger's absolutely correct. I mean, there's sort of there's a move in the standards bodies to have people testing things consistently, so you can make apples to apples comparisons, and I think that's a very good thing.
Well, I don't see any more questions from the audience. And while I'm sure we could probably continue on with this for quite some time more, we are half an hour over our designated time slot. So I think I'll turn things back over to Michelle now to end out the webinar.
That's great. Thank you so much, Sarah Beth and Roger and Tony. That was great. And clearly there was a lot of information there, and we still have over 100 people online. So I think the audience enjoyed it as well. And audience, thank you for making time, even extra time, to stay this long. We really appreciate how lively you were asking questions. If you enjoyed today's discussion, as I said in the chat, please save the date for the next webinar in the series. It's going to be on March 3rd at the same time, and it's going to be an in-depth discussion about the differences between analog and digital dB levels. I'm still finalizing our third panelist, but so far I've got confirmed that long-term AVIXA standards volunteer Pete Swanson will be moderating, and the panel will include Jim Smith of Sound Control Technologies and Tyro Arabel of Engineer Audio Solutions. Look for the link for registration on AVIXA's events page, probably within the next week. Thank you so much, everyone, and I hope you have a lovely rest of your day and week. Bye.
Thank you, everybody.
Thanks, everyone.
Thanks, everyone.